So you're listening to Data Skeptic. And you can imagine that people like you are also listening to Data Skeptic. Would you like your message to reach them or your company's message to reach them? Why not consider advertising with us? Send your inquiries to advertising at dataskeptic.com. Depending on how you want to count it, there's between, one and an infinite number of machine learning algorithms out there. I think of it in 5 or 6 families, your logistic regression-ish stuff, your trees, your support vector machines, your deep learning, etc., etc. It's quite a Cambrian explosion of taxonomy if you want to go deep on it. But more or less, we need a couple of these. Everything else is fighting for the last few percentage, but there's absolutely good reason to have a decision tree in some cases, or a deep learning in other cases, or a logistic regression. A wonderful property we'd like to see in our model interpretability systems is to be model agnostic, not depend on the particular model that was being trained, but to give explanations and insights that are independent of that. Mix in local interpretability, that we could zoom in on a particular use case and say why a decision about that specific case was made with reference to its local neighbors, things that are similar to it. Well, now we've got the ingredients for Lime. Locally interpretable model agnostic explanations. If you've been listening to Data Skeptic since 2016, you might have first heard about these here when we discussed the paper, Why Should I Trust You? And I'm excited to complete that loop a little bit today. Welcome to Data Skeptic Interpretability. Today on the show I welcome back Marco Tullio Imbello. We of course catch up on Lime, but talk about everything Marco's been up to since then and how the model interpretability landscape has evolved. All that and more right after the break. You know, they say knowledge is power, and thanks to the Great Courses Plus, we get to tap into that power with just a click. With this streaming service, you can unlock unlimited access to objective, reliable, fascinating information on virtually any subject. Learn from the brightest minds around the world, benefiting from their years of experience and unique insight. With over 40,000 5-star reviews on the Great Courses Plus, you're guaranteed to find compelling content. This week, I delved into it myself and went into the mathematics section. Mathematics is adjacent to the typical Data Skeptic stuff. We need quite a bit of mathematics to do what we do. We also need some game theory, which I don't talk about nearly enough on the show. So if you want to fill in some gaps, learn about equilibria, start from John Nash and work your way up to auction theory, join me and thousands of other learners by signing up for the Great Courses Plus. Do that at thegreatcoursesplus.com/data. The Great Courses Plus is currently offering Data Skeptic listeners 1 month free. Head over to thegreatcoursesplus.com/data to take advantage of that offer. Nothing to lose. Check out all the offerings. You absolutely will find something of interest. thegreatcoursesplus.com/data. Hey Data Skeptic listeners, we're launching another survey and we'd like your help. If you've got 2 minutes to spare, please take our survey at dataskeptic.com/survey. Your feedback helps us deliver the quality content you can find from Data Skeptic, and you might just win a free t-shirt. So do me a favor and head over to dataskeptic.com/survey and tell us about yourself.
So my name is Marco Tullio Ribeiro. I've been working for the past year or so at Microsoft Research. I'm also an affiliate professor, which is just an honor title at the University of Washington. It just means that I work with students, help supervise students.
Well, it's great to see that you've come so far since when we first spoke and you were I don't want to say just, you were a PhD student.
Yes, I was a PhD student coming out with my first paper.
I hope many listeners will have already listened to or will go back and listen to our first conversation. For those listeners joining us out of order, could you give us a quick refresher on what the locally interpretable model agnostic explanations, or LIME, is?
LIME was a method that I developed during my PhD to explain the predictions of any black box model. Nowadays, there's 100 different techniques for doing that, but at the time, there weren't that many, and LIME was, I think, part of what sparked a lot of interest in this area. Not by itself, but at least it was a paper that was popular at the time.
Yeah, I would say Lime was certainly one of a few tentpole papers that really got this discussion accelerated about model interpretability. You and I will probably talk most about sort of theory and things like that, but one of the things I liked about Lime was that it comes with some source code. Could you tease users about the functionality available there and how they can get going in Python?
Sure. So the open source project allows you to explain any model. So it works for, I say any in quotes, but if you have a model that works for tabular data or images or text classification, you can just plug it in and Lime will explain the individual predictions of that model. All I need is a prediction function.
Well, having a predict function is a pretty low bar, so I should be able to apply the techniques pretty broadly, which is great. It's been my observation that we've had kind of a Cambrian explosion of different methodologies and approaches. Many of them I could say are definitely inspired by Lime, but some of the new ideas also appear very different methodologically. Could you share your take on the landscape of model interpretability options and methods that are out there?
Okay, so there's all sorts of things. First axis that I think we can look at is the type of explanation. In the Lime paper, we talked about different types of explanation, but we really only had linear explanations, so a list of pros and cons. And most of the papers that came out after Lime were about how to compute those weights of pros and cons. So the user would still see the same kind of thing, maybe the weights would differ a little bit. So there's papers on different properties of what those weights should be. All of those would be what are called feature attribution methods or linear explanation methods and so on. So that's one kind. There are other papers that came out with different kinds of explanations. I myself came out with one that we're going to discuss a little bit called anchors, but there are also other kinds of explanations where you have, for example, what are called counterfactual explanations, where instead of telling the user why a prediction was made, you give the user another example with a different prediction, maybe an example that's close to the example you're looking at, to give the user some insight. Oh, if this was different, the prediction would have been different. And then there's yet another kind of explanation, which I hesitate to even call an explanation, but it's when you have the whole model being an interpretable thing. And since then, there's been a whole lot of models that have come up, very interesting ones. They're not based on Lime, they're not inspired by Lime in any way, but they are ways of getting explanations, and there's a whole lot of those.
I was very happy to be introduced to this idea of local interpretability. I mean, first and foremost, because there's good empirical results in a lot of these papers that say, like, yeah, this does seem to have the effects we're looking for. But also, it's just sort of intuitively correct in some way that we can zoom in, understand some local features, how I differ from the global picture, or my neighbors near me are more explanatory about my label, that sort of thing. But what are some of the limitations of Lime or a Lime like approach that demand people look for more general methodologies for other cases?
Yeah, so one limitation is that, as you described, you have this local property, or you're like, I know what's happening around this local region. The problem is that sometimes it's not as clear to the user what that local region is. So maybe you see an explanation and you think you know what's going to happen in other examples, and you think that they're close, but in reality, the model thinks that they're very far. Or Lime considered them very far when creating that explanation, for example. So you may end up making mistakes. You think that you understand how the model is going to behave, and you are wrong, which is really bad. So that's one problem. Another problem that we addressed even in the paper was, okay, you want to understand the model as a whole. Even if you have local explanations, how do you pick different explanations to get a global view? Depending on the model and on the domain, you have more or less success with that. So for example, for the image domain, I think it's very hard after seeing one explanation to get a global view of what the model is doing, because that explanation is so local, like it only applies to that particular image, as opposed to, for example, tabular data, where you see something like, oh, this patient has this symptom. Other patients may have the same symptom, but other images are not going to have the same superpixels or parts of the image that we use to explain, if that makes sense.
Can you define what anchors are and why I might use those over Lime?
So I think anchors as a different type of explanation as opposed to a replacement for Lime. For Lime, what you get is a list of pros and cons. And sometimes what you want is a list of pros and cons. If you want to understand what factors are important for a certain prediction, maybe what you want is precisely a list of pros and cons. With Anchor, the explanation is very different. Instead of getting a list of pros and cons, you get what is a sufficient condition. You get a rule. So for example, let's say that we're predicting someone should or should not get a loan. We predict if they're going to default on their loan, for example. Are they a good payer or a bad payer? A Lime explanation would give you a list of pros and cons. So this person makes a lot of money. That's a pro. But they didn't pay a particular thing that they borrow money this time, so that's a con, and so on. So you get a list of pros and cons. Anchor would just give you a sufficient condition. If the model thinks this person is not a good payer, it would just say the person is not a good payer because they've defaulted on previous loans, for example. It's simpler, it's easier to grasp. It does not tell you what is a pro, what is a con. It just tells you this is a sufficient condition. If you have someone who has defaulted on previous loans, the model is always going to think that you're going to default on the next loan, for example. Hypothetical example.
And those anchors, those explanations, are they taken directly from the features or are they an entirely new idea?
So, given the original example, they are a subset of that example. I don't know if you recall with Lime, we had this distinction between interpretable features and features that the model actually uses. With word embeddings, maybe the model is using word embeddings, but humans are interested in words. With anchors, we have the same distinction. So, an anchor is going to be a subset of the interpretable representation of the example you're trying to explain. So, if you have a piece of text, for example, let's say you have, this is a good movie. Even if the model is using word embeddings, the anchor that's going to come out is going to be a subset of that, maybe the word good, which is saying, look, if you have the word good in the sentence, the model is going to predict that the sentiment is positive, for example. You can change everything else, and the model is still going to predict that. That is what the anchor is saying.
Yeah, so what would be like an adversarial change to that? How else might we say the movie is good?
So this movie is good could be this book is good, this book is bad. But if you keep the anchor good, then you cannot change good with anything else. So if you keep good, it would be this book is good, this movie is good, that movie is good, and so on. You just got at a very important point. You have to specify a distribution. We can't just change everything arbitrarily because, of course, with text, for example, you can always add a word, not. This movie is not good. And then good is not an anchor anymore. So when I say that good is an anchor, that is with respect to a particular distribution. So the user has to understand what that distribution is. And the way we do that with anchors is we show the user what kinds of instances we're computed the anchor over. So we would precisely show them the kinds of examples that would show up. For text, it's kind of hard to generate these examples. For tabular data, it's easier because you can just sample from the original training data according to that distribution. So for example, if you're doing patients and you're doing some medical domain thing, you can just sample, change the patient's age according to the age distribution of the population, change their symptoms according to the population, and so on. And then when I give you an anchor, it's easier to grasp what that means, even if you don't look at examples.
Gotcha. So with regard to the sampling, then, do you take each column and maybe take a random weighted sample from the column values correlated with things, or you sample the whole row, or I guess what is the sampling procedure?
We're not sampling rows, we're sampling columns, but we're not changing one at a time. We're changing everything at the same time. And we have smart ways of sampling, actually. That is part of the technical contribution, where if something, like let's say there's a particular feature that after sampling a few times, you can tell that it's not changing anything. There's no reason for you to waste your cycles and keep changing that to see if the predictions are going to change. So you start with a very wide confidence interval, as it were, for every feature. You don't know if the feature is important or not. After getting a few predictions, you narrow that down. And we use techniques from bandit optimization to do that narrowing in a way that we're guaranteed not to miss things.
So it sounds like we're quickly going to bump into problems of not being able to enumerate all the possibilities and calculate their values and things like that. Is that what led you to bandits, or is there another theoretical motivation?
That's precisely why we went to bandits. You cannot enumerate everything, so we need to, instead of saying, I am sure you can change everything else, you have to make probability statements. You say, with high probability, you can change everything else and the prediction is going to remain the same. And bandits are tailor-made to computing those kinds of things, like to getting at what the subset is with high probability, with the minimum number of function calls as possible. You want to call your black box model as little as possible while still having the probability guarantee.
Very interesting. So it seems like there must be some sort of trade-off with anchors. Maybe if I had one element, it would be broadly applicable but not highly accurate. But something with 3, 4, 5, 6 elements has a lot more support but only applies in specific cases. How do you decide the population of anchors you want to create?
What we do is we establish a threshold. How confident do you want to be? So let's say that you establish that to be 95%, meaning if you get an anchor, the prediction is going to be fixed for 95% of examples. You can change everything else, 95% of the time you're going to get the same prediction. Then what we try to optimize is we want to get the anchor with the highest coverage as possible. Typically that means having less features in the anchor, but it may also mean having less specific features. So if you have a patient, for example, that is really, really tall, for patients that are over 9 feet tall, this is what the prediction is going to be. That's very specific. Like the population is going to be very small that is that tall. Even if you have 2 features, let's say the patient is a male who has this particular symptom, that's an anchor of size 2 that has higher coverage than the previous anchor of size 1. So we want to cover as much as possible while maintaining that guarantee of the prediction remaining fixed, given the threshold.
And what's the stopping condition? What tells me I'm done inventing anchors?
So we do a beam search where we try to find every anchor that satisfies the condition, or as many anchors as possible, and then we pick the one with the highest coverage. That's basically the procedure that we do.
Got it. So I can get more or less by tuning my threshold.
You can, yes. If you want higher certainty, you will need more predictions. You have to explore more.
Ah, bandits indeed. Well, 95 sounds pretty good, intuitively close, getting on the way to 100%. Is that why you pick it? Or perhaps is there a good reason to do some hyperparameter tuning? Maybe I'd want a lower threshold because I'm in favor of more anchors if somehow that's applicable for my application.
So it really depends on how much the users are willing to pay in terms of computation cost and how they're using these anchors. Like if this is going to be a high stakes decision, maybe they wouldn't even want to use anchors in the first place. Maybe you need 100%. And if you need 100%, you should not be using a black box. But maybe you're comfortable with 99% in your application. Then that's how you set that threshold. So it really depends also on the model that you're using. So for some models, with a few predictions, if the model is not too jumpy, you'll get to a high confidence anchor very quickly. But if the model is super jumpy, then you need a lot of predictions. So it really is a case-by-case thing.
And you'd mentioned the trade-off with how much compute you can invest. I presume that's on the training set, or is this after the model's built and you're doing inference?
No, that was actually for inference. One thing that I didn't make clear is that anchor is also a black box explanation technique. We are finding anchors for black box models. So you give me a model and I need to find out what is sufficient about this instance that I'm predicting. And the way I get that is by perturbing and getting predictions. So when you're explaining a particular prediction is when you need to get predictions from the black box model.
So I'm getting really a custom tailored set of anchors to the particular instance I'm looking at. Is that right?
Exactly. That is right.
So that feels very intuitive to me from the natural language processing example, like the word not being present as we've talked about. How does a user experience those anchors in a different setting, like in vision?
So for image recognition, you need a distribution to perturb the image. A lot of techniques, LIME included, what people did was to hide parts of the image and see what predictions you get. With anchors, we went a bit beyond that and we superimpose other images on top. So we have an image in the paper of my dog. There's a beagle there. We're trying to get an anchor for beagle. Why does the model think that this is a beagle? And we want that anchor to mean that you can put whatever you want on the rest of the image, the model will still predict beagle. So what we do is, when computing the anchor, the parts of the image that are not part of the anchor, we put another image in there. So we have fun pictures in the paper where you have the dog's face with sky in the background and the model is still predicting beagle with 95% confidence and so on.
Right. The photos do tell the story effectively, so I definitely recommend people check out the paper. Jumping back to our discussion about bandits, there has to be a reward function, some sort of feedback loop. Do you need users to do that, or can that process be automated?
No, it's completely automatic. The only thing that the user needs to specify is the confidence threshold for the anchor.
And then it's just there from the data that's in the training exercise.
Yes. So let's say that we make a prediction. This is a good movie is a positive sentiment sentence, let's say. And the user says, please give me an anchor. What the algorithm is going to do is going to perturb that sentence in various ways. It's going to say, this is a bad movie, this is a good book, and so on, and try to figure out what it is about this is a good movie that anchors the prediction, hence the name. What it is that keeps the prediction the same even when you change the rest. And that's why it's fully automatic. Those perturbations are happening and we're getting predictions. And at some point, we're like, okay, if I fix this word, the model always seems to predict positive. That is my anchor.
Have you had a chance to get any feedback from users as to what it's like to be given anchors, maybe in contrast to some of the other things you might give them to help with interpretability?
Yeah, so we did a user study actually where we showed people LIME explanations and anchor explanations. And this user study really highlights the trade-off between anchor and LIME and the differences that you get with different kinds of explanations. Because as I was mentioning, a problem with Lime, or a potential problem, is that you see an explanation, but you're not sure of when it applies. When is this going to be valid? Like, I see that this is a positive thing, but when is another example far away enough that it's not in that local region? With anchors, you don't have this problem because the anchor is very precise. It's telling you, if you see this, this is what the prediction is going to be. If you don't see this, you just don't know. So the anchor is giving you more precision, as it were. You know what's going to happen when you see a similar case, similar as defined by the anchor, and you know that you don't know otherwise. And this intuition is precisely what happened in the user study. So when people were presented with Lime explanations, and then we asked them to make new predictions on new examples, what do you think the model is going to do on this other data after you've seen a few explanations? Users with Lime, they were much better than when they didn't have explanations. So we have three conditions: no explanations, Lime explanations, anchor explanations. So when they saw Lime explanations, they predicted more often, and they were right more often. When they saw anchor explanations, they predicted less often, but when they predicted, they were always right. They always knew precisely what the model was going to do. So there's this trade-off. How certain do you want the user to be? How do you want them to be certain about what the model is going to do in new cases, or do you want to have more coverage? And this experiment bears out that with Lime explanations, at least, we didn't compare other kinds, but I think linear explanations in general will have this effect. People predict more often. They are not correct as often as with anchors. With anchors, they're like 100% accuracy or 97% accuracy on new predictions. Humans, that is. Humans are making predictions about what the model is going to do.
Yeah, that's a very interesting point that this paper really helped me appreciate in certain ways. This notion of, I'm not sure if you guys coined this phrase, but I'm going to use it, human precision, which essentially looks at not how well can the human do the task, where we're trying to say, is this algorithm the state of the art or better than human performance? But instead, we're asking, can this human predict what the model's going to do? It's subtle but very interesting about how well that domain expert understands how the model's working. Are you seeing that become a more common metric?
I have seen it used in other papers, and the distinction is really important because in the real world, a user is not forced to make a decision, right? Like after you see an explanation and you see new examples, you can just say, I don't know what's going to happen here. And it's important to qualify that. You don't want to just measure human accuracy, because if the human knows that he doesn't know, that's okay, maybe, depending on the scenario. What's problematic is when they think they know and they are wrong, in my opinion.
So you had mentioned that people who got to see those anchors had a pretty high precision when they were making predictions, but they didn't always make the predictions. What was the mitigating factor there? Why sometimes make a prediction and sometimes not?
So it's very easy because the anchor tells you what the condition is for its application. So if an anchor tells you that the patient has to be over 9 feet tall, you know that a patient that is 5 feet tall, the anchor does not apply, right? Whereas with Lime, maybe I'm telling you, hey, the patient is tall. This is important. You don't know exactly what tall means. Like, is it 7 feet tall? Is it 8 feet tall?
So how did things pan out? There are, I guess, 3 cases: no explanation, explanation with Lime, explanation with anchors. Is there a clear winner here?
So between no explanations and any explanation, there's a clear winner. Explanations help in both metrics. People predict more often and they are more correct. However, between Lime and anchor, you have this trade-off. People with Lime are a little less precise, but they make more predictions. They think that they know what the model is going to do more often. With anchors, they are more precise, but a lot of times their answer is, I don't know. And this depends obviously on the data set and on the model. So for example, with anchors, after seeing one explanation, people made predictions between 25% and 43% of examples. With Lime, it was between 55 and 89. So more than half of the time after seeing an explanation with anchors, they didn't know what was going on. But when they thought they knew, they were right all the time. So there is a trade-off. It depends on what you're using the thing for. If you're using Lime or anchors to debug a system, let's say, you just want to find situations where the system is acting in unreasonable ways. Maybe you don't care about being so precise. You want to find cases of problems. And then in that case, maybe Lime is preferable because it's giving you this list of pros and cons. But if you need more precision, if you want to know what you know and know what you don't know, in that case, I think anchor is preferable. And of course, nothing precludes you from using both.
So accompanying the original Lime paper, you guys released the source code and a Python library that's really easy to pip install and to use to do some Lime work. Since then, I know there's also been some industry adoption and some enterprise tools built. Have you had any observations of what people are doing around the tooling?
Yeah, there's been a lot of use. I personally am not involved in any application of Lime, but I've had a lot of people talk to me from the banking industry. Even at Microsoft, there's a new open source project that encapsulates a lot of the interpretability methods, including Lime and anchors, and puts them in like a dashboard so you can compare all of them. So I know that there's a lot of interest. Companies, for example, Microsoft offers it as part of the Azure machine learning product that they have. And I know that internally, a lot of data scientists use Lime when making their own models and so on. So I think there's been a lot of adoption.
This notion of human accuracy, or how well a human observer might successfully predict what the model is going to do, is a really novel notion to me. And I think that idea really highlights that there are bootstrapping techniques we can do to look outside of just our training and holdout sets about how applicable our model is. Another kind of interesting variant you guys present is in the Our Red Roses Red paper. There are some really neat kind of common sense aspect we might be able to impose on our models. Could you share some details about the research described in that paper?
For sure, yeah. So in that paper, what we're doing is we're saying, look, when the machine learning model makes a prediction, there are certain implications that come out of that prediction, especially for more modern models where the predictions are really complicated. For example, let's say you have a visual question answering system where you have an image and you ask a question. So you have an image, for example, of a bird, and you ask how many birds are in the picture, and the model tells you one. You would expect that if you ask the model, hey, is there a bird in the picture? It would tell you that yes, as a matter of fact, there is one bird. And if you ask the model, are there two birds? It would say no, because there's one. So once you say that there's one bird, there's implications that come out of that. And we thought, I wonder if models follow these implications, if models really, this is crucial to test if they're really understanding what's going on. Because if you tell me that there's one bird, two birds, and no birds at the same time, something fishy is going on. You have to figure out, what is this? So this paper was precisely about this, of given a prediction, and it's specific to question answering models in this case. So if you ask a question and you give me an answer, can we derive the implications that come out of the answer? And once we've derived that, does the model act consistently with its original predictions?
So on the surface, it seems like a couple of simple templates might get us to a certain good extent. Does this image have one insert object? Does it have two insert objects? Does it have more than three? You could kind of quickly enumerate a few options, but if there's not enough variety, of course, the model can just overfit to whatever example you're templating. It seems like this might be simple or deceptively hard. Could you describe the process of building up some of these alternative questions?
So it looks like an easy problem, and I actually thought it was going to be pretty easy when I started out. But it's surprisingly, there's a lot of corner cases that you have to be aware of. We did end up with a rule-based model, but it's not rule-based. It doesn't only work for template questions like, are there X birds, houses, etc. It's a system that uses NLP techniques, like we use dependency parsing and constituency parsing, which parse the sentence into a tree, and you figure out what is the subject, what is the direct object, what is etc. What are the prepositional phrases, and moves them around into implications. It's a quite complicated rule-based system. It's not super complicated, but it is complicated enough that it's not general purpose. It only works for particular data sets. The major contribution of the paper was not this technique of taking a question and producing implications. It was mainly the idea of, hey, we should check the implications and the evaluation of state-of-the-art models. A lot of these models, people nowadays are saying, they have superhuman performance on this task. And when you check these things, you're like, okay, it has superhuman performance on the validation data, but it says that there's one bird, two birds, and no birds at the same time. So maybe we want to investigate that a little more.
Could you describe the process by which you enrich the pool of questions?
So our original idea was mainly evaluation. We want to see if the model is performing reasonably. We do have an experiment where we augment the training data, which is an obvious thing to do. Like if you can generate those implications, you can augment the training data. I don't think that is the right approach though. We do that and we get some gains. The problem is we can only generate certain implications. We certainly cannot generate all implications. It's very complicated. And sure enough, after we generate implications, the model gets those implications right. But what about the ones that we didn't generate? We don't know, and it probably doesn't get them right. So I think we need a technique that enforces that in a different way so that the model is trained to be consistent rather than just adding more training data. That's my hunch, but I also have not produced that model, so I don't know.
In terms of putting some of these ideas in practice, are you envisioning that this be a way of generating out-of-sample testing, or is this sort of an enrichment process that you would imagine machine learning practitioners adopt as just good practice?
Oh, I'd have to pull up an example. Squad has a lot of them. Squad is a question answering data set for text. And some of the questions are really long. So it will say, when did this person die after the potato famine in Ireland in 1987 or something? I'm making this up. But figuring out how to move that, like in 1987, like you can guess that you can create a rule, oh, that indicates a date. During the potato famine also indicates a time. So if you ask a question, when did X happen? Was it in 1987? Is that the correct answer? Or was it during the potato famine? Or was it during the potato famine of 1987? Piecing those together automatically is not trivial for when you have really complex questions like that.
Yeah, that's interesting. Do you have any examples of outliers or corner cases or just interesting boundary use cases?
That concern of overfitting is precisely why I was saying that I don't think this is the right approach to just add more training data. Sure, we've identified this problem, but it is indicative of a more general problem of, are our models really generalizing? Are they learning? And when will we know that we've really achieved a model that really understands things? That's above my pay grade. But that's what I'm working towards, trying to figure that out.
So one might take the perspective that this is a flaw you're pointing out in a lot of question answering systems. We can develop these enrichment processes and give them more questions to answer and more challenges, and maybe the techniques, a little bit of encouragement, figure everything out. Or maybe the techniques will just overfit to the couple of ways we've figured out how to enumerate new questions. What are your thoughts on, I guess, how this cat and mouse game evolves?
So if you apply LIME, this is a case where interpretability may not help. It may help and it may not help. In this case, I actually think I know why the model thinks there's 1, 2, and no birds. Here's why. In the original data set, 10% of the questions have an answer that is a number. So how many birds? 1. It's something like 0.03% have numbers in the questions. Most of the data set does not have questions that contains numbers. The numbers are always in answers. So models trained on this data set do not learn how to reason about numbers when they appear in the questions. They learn to reason about numbers when they have to answer numbers. And if you use a technique like LIME on anchors, it's going to tell you what drove the prediction of 1, 2, or 0, or no, and so on. But it's not going to give you that insight to go back to the data set and figure out, okay, what is happening then? You need that additional step. You would need some ingenuity from the data scientist to go and check it out for this particular problem.
So how can model interpretability techniques help us figure out why this model will think there are simultaneously 1, 2, and no birds in a picture? So we're not fully automating ourselves away yet then?
Not yet.
Excellent. Well, Marco, what's next for you in your research and work?
So I see my work as providing an interface between human and machine learning. So explanation is obviously an interface. You're explaining what the model is doing. This paper with consistency is also a bit of an interface because it's evaluation. It's getting at, like, is the model really understanding what's going on? One piece of work that I'm really excited about, it's ongoing work under submission right now, really gets at the trust issue of, is the model working? I can't give too many details, but what we did in that paper was to take software engineering insights and apply them to machine learning. So think about unit tests, for example. When you write a piece of software, everyone knows that they're supposed to write unit tests. Not only that, there's a lot of guidance as to how you write unit tests. So test boundary cases, test invalid inputs, test each individual function, and so on. That sort of thing does not exist for machine learning. What we do is we get a huge data set and say, what's the accuracy? 95% or something. This ongoing work is really about developing these principles for machine learning. In machine learning, you cannot test individual functions because the model is a unit, a black box. But can you test individual capabilities? So for example, this paper we just discussed is testing if the model is consistent. You can think of a whole host of other properties to check, of other properties you want to check. So to give an example, we were talking before about the medical domain. Let's say that you have a medical diagnosis system. A property that you may want to check is, hey, if my model makes a prediction for a patient, changing that patient's age by 1 or 2 years should not change that prediction. That is a test that you can write, and you can check that for every prediction your model makes. Does it behave according to that property? Or another test that you may want to add is, let's say I'm doing sentiment analysis. If people start swearing at the end of their emails, sentiment should only go down. It should not go up. For example, I'm not saying this is a good test, but you can have properties like that you should check. And right now, we don't have this engineering culture of writing these tests and checking models with them. And I'm hoping that's going to change. So that's a paper that is coming out, really excited about. Another direction, still thinking about that interface between humans and machine learning. And I'm actually a little embarrassed because I promised that this was a direction last time when you had me 3 years ago, and I didn't make any progress on it, but I am actually actively working on it right now, is feedback. So once you've identified a behavior in the model, my model is not doing what is right, or my model is not doing what I want it to do, how do you fix it? Right now, you basically need a PhD in machine learning to fix it. You need to go and get more data or create a new type of model or change your model. Like, it's really hard to get the model to behave how you want it to. And we don't have, in my view, really good techniques for giving punctual feedback. Say, hey, don't use this kind of feature, use this other kind of feature. Or if you say there's one person, there should not be two. How do we say that to models nowadays? It's really hard. So this is a direction that I also think we need to make progress on.
I might be bringing my own bias to the table, but I'm very excited about that idea you'd mentioned of bringing the notion of unit testing into the machine learning world, that, surely this case must turn out this way kind of stuff. I'm curious, operationally, do you envision that being something that, there'll be a quality assurance engineer will be capable of writing, or are these things that data scientists will manage in most cases?
Will it be a quality engineer? Do we require ingenuity? Part of the contribution that you can imagine is helping humans come up with these tests. So you can imagine the system even suggesting, hey, is this a property you think is good, or is this not a property that makes sense? And in the paper, we actually have something like that where we suggest certain things to users. We help them come up with things by giving them guidance and also by giving them suggestions. So I don't know who's going to be doing it, if it's going to be a quality assurance engineer, if it's going to be the domain expert, if it's going to be the machine learning engineer, or if it's going to be all of them, each of them with different kinds of tests. I imagine all of them.
Well, it's a lot of exciting ideas, and I'm eager to see how that plays out and gets adopted in industry and see what the literature looks like as these ideas get explored. Anyway, Marco, it was great catching up with you. Thanks again for taking the time to come on the show. Where can people follow you online?
I am not a very good social media person. Best way to find me is on my website. I update it somewhat regularly, and I think you have a link at the end of the show. Thanks, I really appreciate it. Thanks for having me on.
Thanks for listening to Data Skeptic Interpretability. Our guest today was Marco Tulio Rebelo. Our theme song is Number 5 by Big D and the Kids Table. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. I've been your host, Kyle Polich. Thanks for listening, everybody.